Hello everyone, this is Professor Iris Miano giving you day 19 lecture on sections 7.4 regarding functions and section 6.1 regarding scatter plots for Math 50 pre-statistics. And here we go. Let's start with the functions section, in which the first thing we will be defining is a relation. Now a relation generally is defined as a set of ordered pairs. So let's go ahead and put that down. Let's get my drawer ready. A set of ordered pairs. And certainly relations can have that sort of a feel to it or look to it. They could look differently than that, and I'll show you a few examples of that. The domain is the set of all values of the inputs, commonly called X as well, and the range is the set of all values of the outputs, or Y. All right, so we have a couple of examples of relations here. So notice in numbers 1 and 2 we have curly braces with a set of ordered pairs inside of them. So that is considered to be a relation, and we want to, just for this example, identify the domain and the range. So the domain is it usually has this set notation to it where we can define it as X such that X is equal to either -1. So we're just going to take all of the X values in the ordered pairs, which are all the first values within each set of parentheses. So -1, 2, 0, and -1 occurs again. Okay, so since -1 was already listed here, it's customary not to have it repeated. Okay, oops, and that was a very sloppy, what's it called? Curly bracket. And furthermore, it's kind of conventional, so I'm going to uphold this convention of putting all of the values in your list for the domain in order from smallest to largest. So I'll go -1 first, which is repeated, but I'm only going to list it once, then 0, then 2. Okay? So that's like the ultimate, like, fanciest way to state the domain. And so that'll be the domain of the first exercise. The range is going to be all of the Y values listed. So all of the second values in each ordered pair. And by ordered pair, I mean within each set of parentheses. So that'll be all Y's, such that Y could be equal to 2, 4, -5, and 3. So we have 4 distinct values, and let's go ahead and on the way, let's go ahead and put them in order from smallest to largest. So the smallest one's -5, then I believe 2 is the next largest, then 3, then 4. Cool. So that'll be the domain and the range for number 1. For number 2, the domain will be X such that X is equal to, let's see, we have -4, -2, 3, and 5. So 4 distinct values, and they happen to be listed in smallest to largest order as I read them from left to right. Now remember, the domain is just the X values of the ordered pairs, or the inputs, and so we'll just be grabbing those first values within each set of parentheses, -4, -2, 3, and 5. The range is going to be the Y values for each ordered pair. The Y's such that Y could be equal to 1, -3, 0, and 1 is happening again. Check that out, okay? So 1 is repeated, so we'll only list it the once, but the smallest range value is -3, so I'll list that one first, then 0, then 1, but just mention it once, okay? Cool. So there we go. That's how you'll present the domain and the range for your relations. Now, certain relations meet the criteria of being a function. A function is a relation that that each input leads to exactly one output. I just want to make sure I have the wording right, because there's a lot of confusion surrounding the definition of a function. A relation that has each input leading to exactly one output. Said another way, if you ever have one input mapping, which is another way of saying going from input to output status, if you ever have an input mapping to two separate outputs, that violates the definition of a function, and therefore the relation cannot be defined as a function. So in the next example, it says, for the relations above, which is a function and which is not a function, and explain. So what I think would be proper to do for this is, instead of ordered pairs, I want to come up with a more of a visual representation of going from an input to an output. And I'm going to change up the colors because I think that would be really helpful for this endeavor. So I'll have the inputs listed in green. So those are your X values, and we'll go Y's in red. X, Y. Oh, and I'll do this for both. And we'll have the mappings be in like black or something neutral. Okay, so let's first list the x's. So the x's was -1, 0, and 2 for the first relation. And the second relation, I'll list those x's as well. We'll just do them both at the same time. -4, -2, 3, and 5. And setting them up vertical is kind of conventional here. Okay, now for the y's, go ahead and do the same. List them vertically. -5, 2, 3, and 4 for the first relation, and then the y's for the second relation were -3, 0, and 1. So in black, I'm going to draw the connections from inputs to outputs, and that'll be dictated by each ordered pair. So for the first relation, -1 mapped to a 2, so I'm going to draw a arrow pointing there. 2 mapped to 4, so 2 maps to 4. 0 maps to -5, 0, -5, and -1 maps to 3 as well. -1 maps to 3. Okay, now before we talk about if it's a relation or if this relation is a function, let's just go to the next one over, okay? So let's make all of the connections here. So -4 maps to 1. Like so. -2 maps to -3. 3 maps to 0. And 5 also maps to 1. Okay, so we want to take a look at these two different visuals. And I think coming up with this like a chart like with the mappings and arrows is a little bit easier to see which one's a function and which one is not. Okay, so notice in relation 1, which I'm hovering over my mouse with, okay, we have one input of -1 mapping to two separate outputs of -5 and 3. Now, that is like, so my analogy here is like meeting up at a Starbucks. Let's say that the input is, you know, some person, and the output is the process of meeting up at a Starbucks. So what is happening with this -1 person right here is they are trying to meet up at two different Starbucks at the same time. That doesn't make any sense as far as, you know, what could happen in real life, right? Whereas over here, we have person -2 and person 3, they're just going to their own distinct Starbuckses, whereas person -4 and +5, they're meeting up at the same Starbucks. That's fine as far as function definition is concerned. Two outputs can map to this, two inputs can map to the same output, but we can't have one output trying to map to two separate places in the output area, okay? So for that reason, we'll say relation 1 is not a function. since -1 maps to two separate places, two separate outputs, and relation 2 rather, is a function because it doesn't have any inputs mapping to two separate outputs, because it does not. Have any inputs mapping to two outputs. There we go. We can discuss this more in class if you'd like, just let me know. Okay, now let's talk about graphing functions. So a graph represents a function if any vertical line basically passes this vertical line test. So the test goes like this. If the trajectory of your graph passes a vertical line, if the vertical line, that is, passes through the trajectory more than once. Oops. Let me try that again. Where's the eraser? Trajectory more than once. Okay, so I do have a soft, flexible, straight edge that I'm going to try and use to make good vertical lines. So what would be a good contrast color to this blue? I think like orange would be really good against it. So concerning this first graph, this is actually a cube root relation right here, and we want to test to see if it's a function by implementing the vertical line test. So it goes like this. If I can draw a vertical line such that it passes through the blue trajectory more than once, then I say, oh, it's not a function. So here are a few representative vertical lines in orange. I just want to see, is there any instance in which this blue line crosses more than once on any of those vertical lines? Well, no. And in fact, there's not a vertical line possible that can be drawn even on top of this y axis, right? It looks like it might cross in 2 points, but nope, it only crosses the origin just the once, okay? So there's no possible vertical line that could cross the blue trajectory more than one time, so we'll say it's a function. Okay, so the first one's a function. Cool, cool, cool. Now, the second one, this oval shape, notice that I can draw one vertical line. Here's an example vertical line right here in which it crosses twice over, you see? And I'm going to just really highlight the crossings with big dots right there. So this is an example of a relation that violates the vertical line test. So by virtue of that, having a vertical line that can cross it more than one time, that means that this relation is not a function. So what do you suppose is happening with this last one? Is it a function or is it not a function? Can I draw a vertical line that can pass through the blue trajectory more than once? Yes, and here is an example. There's a vertical line, and it is passing through the blue trajectory once, twice. It could also pass more than twice and still, violate the vertical line test. It just has to pass through more than once. So this one is also not a function. Moving on. Function notation. Now this is something that can be very confusing. Let me change the color up real quick just to make it a little bit easier to read. Let's make it this beautiful magenta A color. Function notation is given by the following. Your y, your output value, is now going to be replaced by f of x or g of x or n of t. Basically, it's some letter on the outside and then some other letter on the inside, where the inside letter is your dependent variable, acting like your x. It could have a different letter to it, though. And the f or g or h, the function name could be different than f, although f is the most conventional one. That's basically the function name. So one thing I want you to know is that this is f of x is not variables f and x multiplied by each other. Nope, this is not representing multiplication here. It's a totally different idea behind this notation, although it shares the same type of notation as two variables being multiplied together by virtue of the use of the parentheses. So it's your job now to understand this new context and see this f of x as an input of x into a function called f, okay? Is not variables multiplied together. So f is the name of the function. And x is the input. I think it'll become clearer how this function notation works after some practice. So let's go ahead and dive into that on the next page here. Let's say we have one function named f whose input is x, and it is governed by taking your input and multiplying it by a 2, and then adding 7 to it after the multiplication has happened, okay? That's how function f works, okay? Function g, on the other hand, has the same input of x, but its output is -3 all the time, no matter what the input of x is. So g of x is kind of a real super funky, strange function, but it's still a possible function. It is just making sure that all of the outputs ever, no matter what the input of x is always, the output is always going to be a -3. So anytime you see a g function, you just get to say it's equal to -3 and not perform any calculations. However, the f function has calculations based on what you plug in for x, okay? So f of 2, for instance, for our first example, that's going to be taking your 2 times the input and adding 7 to it. So one way that you can deal with this is just to say, okay, anytime I see an x in the f function, I'm just going to leave some open parentheses, and whatever is inside of my f function, in this case a 2, that's what I'm going to put inside of any open parentheses. So then I will, use order of operations to simplify this down, which will say I'm going to multiply the 2's first to get 4, and then I'll add 7 to it subsequently, and that'll give me 11 as my final answer, okay? Cool. Let's go to number 2. Let's use that same f function, but now the input is going to be a -6. Now how will that look? Well, I'll still start off the same way. The f function is 2 times the input plus 7, but what's the input now? It's -6. All right, so then, just like we did in the other example, we're going to start by multiplying the 2 times the input, which will be the -6. And we will get -12 plus 7. -12 plus 7 is going to yield a -5. And that'll be it for that one. Boop. Okay. Now moving on to number 3. Number 3 is one of the tricky ones. It's so easy, it's hard, okay? G of 2, guys. G of 2. Are there any x's in the g function? No. It doesn't matter what the x is. It could be 2, and we'll see later on with number 6, it could be -1/2. The output is always going to be just a -3. Call it done. Seriously, there's nothing to do here because there are no x's in the g function itself. Okay? Cool. Let's do some more practice now with f, going to number 4 here. Remember, f hasn't changed its structure. It's still 2 times whatever the input is plus a 7. But what's the input this time? It's 3/4. Okay, So now do what you need to do in order to make this multiplication happen with this fraction input. Maybe put that 2 over a 1 if it's helpful. Cancel out common factors. 2 goes into itself at once, goes into the 4 twice. And then we'll be left with what? That'll be 3 halves plus 7. Okay, so that 7, you can put it over a 1 and do some building up so you can have a common denominator. So you can actually add those two items together. Okay, so that'll give you 3 halves plus 14 halves, which equals 17 halves. You can leave your final answer like that. I'm perfectly happy with that. Or if you're like, I need to turn this into a mixed number, by all means, you know, call it your, what, 8.5, I believe is what you'll get. You could turn it into a decimal, but why do all of that extra work? There's no need to. Just leave it in the final form, provided that this fraction is already simplified as far as it can be, and it is. So that's why I have it boxed up. Okay, let's do another one with a fraction input. Negative fraction input this time. So that'll be, I'll just do this one down below because I kind of encroached on this space here. Remember, f is 2 times the input plus 7, but the input this time is negative 5 halves. Cool. Do the same thing, I would recommend, in order to perform this multiplication. Put that 2 multiplier out in front over a 1. Cancel out those common factors of 2. Recognize that this first term that settles down is going to be negative because there's a negative factor in there.